Name is Cam Himes, and I'm going to be talking about wavelet trees. For an agenda, I'd like to cover wavelet tree construction, just the general algorithm. I'll go over an example for that. Talk about rank and select query algorithms, how those work as we can traverse a tree to find this information. I'll talk a bit about a couple of methods for wavelet tree compression to take better advantage of some of its properties to reduce the space needed. And then I'll cover a couple of interesting applications to solve problems. So as an example, we can consider a string S, which is Mississippi, one we've considered a lot in this course. You can see that Mississippi is made up of 4 characters, M, I, S, and P. So we have an alphabet sigma of length 4. So step by step, what we're first going to do is take that alphabet and partition it into 2 separate parts. Here I'm using 2 equivalently sized parts. They're both of length 2. So the first one, which I've color coded with blue, it has I and M, and the second one has S and P. Now we're going to represent the string as 2 subsequences composed of these separate alphabet subsets. So all you can see here is really the color coding, but you can see that anywhere there was an I or an M in the original string, I've color coded it blue. So those first 2 characters, MI, are blue. And then anywhere there's an S or a P, I've color coded it red. So it's MI in blue, SS in red, and then I, and then SS, and so on and so forth. Next, we're going to represent the string with a binary encoding. So we're going to take that string and turn it into a bit vector where any characters in the first partition, IM, become 0, and any characters in the second partition, SP, become 1. And again, I'm using the color coding here for clarity, but you can see that all of the M's and the I's became 0s, and all of the S's and the P's became 1s. So the string, which started as Mississippi, now becomes 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. Next, and I just have the same information up top for clarity, we can separate the 2 subsequences based on their membership in the partitions to create our first split that is going to define our wavelet tree. So I basically just took out these characters to create 2 separate subsequences of the original string. We have M, I, and SSSSPP. And now what we're going to do is we're going to repeat steps 1 to 4 for that MIIII string and the SSSSPP string until the size of the alphabet we're working with becomes 1, at which point we will be left with a single character in each of the alphabets, and that single character will become a leaf of the tree. Now for visualization, I've got this example pulled up. So as you can see, we have the initial value, Mississippi, and the initial split, IMSP. So we took that string, we created a binary encoding, and then we performed our first split. You can see that the left edge is labeled with a 0. This is just convention. And the right is labeled with a 1. So on the left, we have a new subtree. And this node that starts this new subtree just has the characters from that first partition. So M's and I's, M, I. And now you can see we repeated that step. So we have in this substring the characters I and M, and now we've taken that and partitioned it once more to create 2 more alphabets, each of length 1, and another binary encoding where the M is represented by 1 and the I's are represented by 0s. So we do one more split and we're left with leaf nodes that are just labeled the same as the individual character in the alphabet that we created, alphabets. So we have the leaf nodes I and M. And on the other side with the S's and the P's, we've done the very same thing. We've taken it, that alphabet of S and P, and split it into 2 separate alphabets, S and P. We created a binary encoding and split it, so we're left with the leaf nodes. And at this point, we're done. But it begs a question as to what information is really stored. Because I've added some additional information here for the sake of clarity, but we don't really need all this in the wavelet tree representation. So what we're going to end up with is in fact something like this, where we're just storing the bit vectors at each level, and then we have the values of the edges, but we are not explicitly storing the original string. So we're not storing Mississippi, we're not storing MMI. We don't have something explicitly denoting the split. It's just clear where it splits. Okay, let's talk about rank queries. So if you recall, rank is a function we've used a few times now, taking a parameter I representing some position and a parameter C representing some character, And it's going to return the number of occurrences of the character C up to the ith position in the text. So for a wavelet tree, we have this pseudocode. It says if L is equal to R, then return I. And so L and R are formally part of the function call, but for the sake of simplicity, I'm omitting them, so not explicitly stating them. But L and R basically represent two indices. And these are not indices of the original string, so it's not like we're considering a substring within Mississippi, but they're instead indices describing a subset of the alphabet, which we're considering. And in our wavelet trees, if you recall, if we go back, essentially at each level of the tree, what we were considering, although it was never explicitly stated, is an L and an R. So at the root node here, L is equal to 0 or 1, depending on what kind of indexing you're doing, and R is 3 or 4. And basically, I'll go with 1 and 4. We are looking at the entire alphabet of 4 characters. And then in this left split, we are considering these first 2 characters, if you've sorted the alphabet lexicographically. So that would be L equals 1, R equals 2. This would be L equals 3, R equals 4, and so on and so forth. So what we check as part of this function is that if L is equal to R, we are going to return I. So I is the position passed into that current rank call. That's kind of our base case. What we're going to do otherwise is compute some middle value m, and m is going to be equal to the floor of L plus R divided by 2. So it's essentially right in the middle of L and R, or as I've said, the middle point of the node we're currently considering. And then we're going to compare C against the character stored in the subset of the alphabet at position M. And then I'm not going to explicitly go through this because it's a bit formal, but we're using this check to determine whether this character we're considering is in the left subchild or the right subchild. And so that is going to guide our next rank query. And we're basically going to start at the root node, so with L equal to 1 and then R equal to lowercase sigma, the size of the alphabet. And we're going to work our way down the tree until we reach a leaf node, which is the point at which L would equal R, because the size of the alphabet then would be 1. And then we can return the position. So to make this clearer, I have an example. Here is a wavelet tree, not for Mississippi, but instead for a Burroughs-Wheeler transformed string. And keep in mind, as I previously said, the wavelet tree only has access to the bit vectors. But for the sake of illustration, I've included explicitly the partitions as well as the strings. And this looks quite a lot like the Mississippi split in that it's a balanced wavelet tree. First, we split the dollar signs and the A's off to the left and the C's and the T's off to the right. And we end up with leaf nodes $A, C, and T. So suppose we want to compute rank with parameters 7 and A. So we want to know how many A's occur up to position 7. So first of all, we're going to start at the root. And what we can notice is that A is in the left partition along with $. So it's going to be represented by a 0 in the bit vector stored at the root. So what we're going to do is we are going to compute the rank up to the 7th position of 0 on this root bit vector. And here we find it's 3. So this says that up to position 7, there are 3 zeros. However, that is not our final answer because, based on the partition, it's clear that the zeros here in this bit vector can either represent a $sign or an A. So there's kind of ambiguity. And so what we do is we move on, and we're going to be moving on to the left child because A is in the left partition. So moving on to that left child, we have the A's and the $signs. And here we're taking our previous answer, 3, and passing that in as the first parameter of rank. And in this case, A is in the right partition by itself. So instead of looking for zeros, we're looking for ones. We're seeing basically in the first rank query, we determined that in the first 7 positions, there are 3 zeros which are passed down to this left child. Those zeros can either be A's or $signs. So in this second rank call, the second rank function, we are looking to see how many of these 3 zeros, which represent the first 7 positions of the original bit vector, represent ones, which are A's. And here we find it is 2. So if we just look at the first 3 characters of this bit vector, 2 of them are ones. And now we can move on to the leaf node, which we knew is to the right because of the A being in the right partition. And the fact that we reached a leaf node indicates that our previous answer, 2, is the final answer. And in plainer English, that's the case because whereas there was ambiguity with the first rank call, the zeros could represent either $signs or A's. If we've reached a leaf node, it means that whatever rank query we did previously is, there is no ambiguity. Like in this previous bit vector, the ones can only represent A's because it's by itself in that partition. So that's how you can run rank. So for select queries, we are working with a very similar select function, which also takes, like rank, a parameter I representing a position and a character C. And it's going to return the position of the ith occurrence of the character C in whatever our text is. Similarly to rank, I've omitted it for the sake of simplicity, but often we'll be working with a Burrows-Wheeler transform string. And we are also sort of implicitly passing in an L and an R value, which denotes not a subset of the original string, but a subset of the alphabet, or in other words, a node. So just like with rank, we are going to be making a lot of select queries to run select across the entire tree. So for an example, we can use that same wavelet tree, which we've just gotten accustomed to, and we can run select to T. So this is essentially asking, if we recall our definition, the position of the second occurrence of the character T. Now in the wavelet tree, I have, still for illustration purposes, the entire string. Keep in mind, the entire string will not be available to the wavelet tree itself, so to speak, but we can manually count and see that the second T is in, using one indexing, 1, 2, 3, 4, 5, 6, the 6th position of the text. So that's what we expect our answer to be. But unlike with rank, we're actually going to be starting from the bottom of the tree from a leaf node and going up to the top. Specifically, we're going to be starting with the leaf node, which represents the character we're looking for. So in this case, with T. You can see that T is in the right partition here as a leaf node, so it's represented by 1 and the bit vector of its parent. And in general with this tree, as with most trees, there's only one parent for this node, as for all nodes, so we only have a choice to move up to its parent. And here we're going to run a select query, slightly different than the original one. We are still looking for the second occurrence, but this time not of T because we only have the bit vector, instead for 1 because a 1 represents a T, as we saw. And we find that it is in position 3. So this bit vector, which we'll see in a second is connected directly to the root of the tree, contains all T's and all C's. That's just the nature of the wavelet tree. So the thinking is that if we can find the second position, the position of the second T here, we can use that to find the position of the second T in the overall string. And this is something which I didn't mention explicitly in talking about rank queries, but it's true for both. We're kind of trying to account for the fact that these bit vectors only represent a subsequence of the original string. So that's why, even though the answer for this is 3, we can see that looking at these characters that the second T is in position 3, 1, 2, 3. That's not the final answer, because this does not represent the entire string. So if we return that as the answer, the position is not going to match up, so to speak. So, okay, we take that answer of 3 and we move up to the parent. And now we pass that in as the first parameter. So we're looking again for a 1 because a 1 here represents a T or a C. And specifically, we're looking for the position of the third occurrence of 1. And we're looking for the third occurrence of 1 because we know that that third 1, which came down here and became something else in the bit vector, represents the second T. So this is us accounting for the position. And here, we can count it out. And we find that it's at position 6, which is the answer that we anticipated. And seeing as how we've reached the root, we have nowhere farther to go. So this is going to be our final answer. So really, it's quite similar to select, just a little bit different because we're looking for different information. And a bit different in that we start at the leaf, so there's no ambiguity, and then we work our way up to the root, accounting for the position differences at each step. Now, in terms of runtime complexity, I first want to note that the tree height is assumed to be the ceiling of log base 2 of sigma, lowercase sigma, the size of the alphabet, assuming a balanced wavelet tree with even alphabet splits. So as you go down the tree, there will ultimately be sigma leaf nodes, and so the height of the tree is going to be log base 2 of sigma, because at each position you're kind of halving it. So for rank, we're traversing the tree from the root node to a leaf node. And at each level of traversal, we use pre-computed rank support structures, which I didn't really mention, but on the bit vector to compute rank in O of 1 time. And I'll talk about those a little bit in a second, but this is just referred to as Jacobson's method. He's the one who discovered it. So therefore, we're performing a constant time in O of 1 operation log base 2 of sigma times, because that's the height of the tree. So the worst case for runtime is simply big O of log sigma. Very similarly for select, we are traversing the tree, this time from a leaf up to the roof node, and at each level of traversal, we use pre-computed select support structures on the bit vector to compute select in constant time. I said this is Jacobson's method. I believe this is actually Clark's method. Therefore, we're performing a constant time operation, very similarly, log base 2 of sigma times, so the worst case runtime is the same, big O of log base, log of sigma. Now, in terms of the space complexity, the overall here is n times the ceiling of log sigma plus little o of n log sigma bits. So the first term here, the bigger one, n log sigma, represents n times the ceiling of log sigma, represents the space needed to actually store the bit vectors. So there are log sigma levels in a balanced wavelet tree, which we discussed. Now, for each level, we have 1 bit for each character in the input string stored as separate bit vectors. And what I mean by that is if our original bit vector, our original encoding of the string is 11 characters, which would correspond to a string of 11 characters because each one becomes 0 or 1, then as we go down the tree, we are going to have these characters split up into separate bit vectors, but they're all going to sum to 11 each time, all the way down to the very last level before the leaf nodes. So the total space across all levels to store these bit vectors is n times the height of the tree log sigma bits. The second term, O little o of n log sigma, represents additional but sublinear space needed to support these constant time rank and select operations on the bit vectors. Each of these structures is a dictionary, essentially, of size O little o of n bits for each bit vector. So since we have the ceiling of log sigma levels, the cumulative space that is needed for those support structures is a little o of n times log sigma for an overall space complexity of O in log sigma. Now, these support structures I'll mention briefly, not really in detail, but they're very similar. The rank support structure is a sampled hash map, which I believe we've discussed in class, which stores pre-computed counts of the rank, the zeros and ones up to each position in a bit vector. The keys for this dictionary hash map are the interval positions, and the values are the cumulative counts of zeros or ones. So basically, when you want to access something, you can pass in a position, and if it exists in the hash map, then you can immediately grab it. If not, you can make some very small number of steps, depending on how frequent the sampling is, in order to, in constant time, get the value you're looking for. So this enables constant time rank queries and uses little o of n bits per bit vector. Very similarly, select is stored in a hash map where we have keys for internal counts. Also using sampling here, and the values are positions. So this enables constant time select queries. In terms of wavelet tree compression, there are 2 ideas I'm going to mention here. I know there are more, but the first is entropy coding, and the second is actually changing the tree shape. So for entropy coding, I would suggest looking at a string like AAB, AA, $BACA. So looking at this, clearly the character A is dominant. It appears more frequently than B, C, or the $. And this difference in character frequency, just generally speaking, indicates the potential for compressing the bit vectors. So the basic idea is to compress the bit vectors in the wavelet tree using a zero-order entropy coding method like run length encoding. So zero-order entropy compression sort of explains the minimum number of bits needed to encode a sequence based on the frequency of the symbols. In our case, we have bit vectors, so we're just thinking about zeros and ones. So we can use run length encoding to take a vector which looks like 11110000 and store it as 1404, meaning there are 4 ones followed by 4 zeros. After compression, I think we'd have to adjust the rank and select support structures a bit to ensure efficient operations across these compressed bit vectors, but we could still allow for constant time queries. And with this method, we can achieve a space complexity of n h sub 0 of s bits, where h sub 0 of s is a function computing the empirical zero order entropy of a sequence S. Another option for compression is changing the tree shape. So as a basic idea, we can use what's called a Huffman-shaped wavelet tree instead of the balanced one, which we saw with previous examples, in order to reduce the storage space and improve the average query time. So a Huffman-shaped tree, just in general, is going to split the characters at each node such that the frequency sums of the left and right child nodes are as balanced as possible. So more frequent characters in this construction should be closer to the root of shallower depth, basically, which is going to enable faster access for common queries because we don't have to go through so many levels of the tree. So as an easy example, we can consider a string like AAAA, BBB, CC, DD, E. So in terms of the frequencies of the individual characters, there are 4 A's, 3 B's, 2 C's, 2 D's, and 1 E. So in our first partition, what we're going to do is try and come up with 2 partitions of the alphabet such that the sums of the characters in each partition, the sums of their frequencies in the original string, is about equal. And here we can achieve that quite well. So our first partition is AC. So the frequency of A is 4, the frequency of C is 2. 4 plus 2 is 6. The second partition, BDE, the sums of those characters' frequencies are B3 plus D2 plus E1 is 3 plus 2 plus 1, which is also 6. So the left child and the right child are made up of characters which have frequency 6. At the left node, AAAACC, at this point, we just split it off into A into C because we only have these 2 nodes here, so really there's no choice. And I think it's somewhat arbitrary at some point if there's some sort of tie, but generally I think the more frequent character goes in the left partition. At least that's what I've done in this example, which is why A is in the left child and C in the right. And then in the right child, considering BBBBDDE, here the frequency of B is 3, and the frequency of D plus E is 2 plus 1, which equals 3. So again, we've achieved an equal split. So B is immediately split off into its own leaf node, and then we end up with DDDE. And then those are split into leaf nodes as well. So this method can achieve space close to the entropy coding method. And when rank and select queries are run on characters in proportion to their frequency, basically meaning more frequent characters are queried for more often, and the same is true in inversely, then common characters have reduced average query times compared to balanced wavelet trees. As a limitation, the worst case can become worse for infrequent characters as they have longer paths. So just looking at this, we would hope that someone would be querying for A the most often because it's the most frequent character, and then after that B and the C and D and E. And so you see if you query for A, for example, and this is a relatively small example, so it's not that much of a time save as compared to a balanced version of this wavelet tree. But with A, you only have to go down 2 levels to do a rank or select query. Whereas with a character like E, which is very infrequent, you'll have to go down 3 levels, so it's a bit worse. Finally, I'm going to cover a few problems that we can solve using wavelet trees. So the first application is counting occurrences in an interval. Given a string S in interval I to j and a character C, we want to find the number of times that C occurs within this interval S from I to j. The basic idea is to check the rank at the end position and subtract the rank at the starting position -1. Suppose we're looking to see how frequently the character C occurs within the interval 3 to 8 of some string we've created a wavelet tree for. The occurrences of C within that range is equal to rank C of 8 at position 8 minus the rank of C at position 2, 3 minus 1. And ultimately, for our previous example, this evaluates to 1. Now, in terms of runtime, we've previously determined that rank is a O of log sigma operation. So we're traversing down the tree, and since each level of the tree requires a constant time rank operation, and there are log sigma levels, at least in a balanced wavelet tree, the overall runtime is still big O of log sigma. Now we can adapt this to count occurrences within a subset of the alphabet in an interval. So given a lot of the same starting points, a string S, an interval I to J, and a subset of the alphabet A, we want to count the total occurrences of all characters in A within this interval. So for each character in A, we can just defer to the previously described algorithm and sum the results of that algorithm for each character to get the final result. Now, since the previous algorithm runs in log sigma time, and we have to run this algorithm for each character in A, the runtime of the algorithm is simply big O of the size of A, the size of that subset of the alphabet, times log sigma. One final problem is kth smallest element. So, for example, if we want to know what is the third lexicographically smallest character that appears in the subarray from index I equals 2 to I equals 8. So working again with this same wavelet tree. First we can look and say, well, from 2 to 8, actually this is the string, and we wouldn't know this based on the wavelet tree, but we know now. It is $ATCA. So first we can count how many elements go to each child in the range from 2 to 8. So this range we're considering. And we can use this previous algorithm we've described. So we take the rank of zeros for this substring $ATCA at 8, and then subtract the rank at 1. So we're finding it in the interval as previously described. And in this case, we find that there are 4 zeros here, and there are 3 ones. So since the first 4 smallest elements go to the left child, we're going to move to that node because the third smallest element that we're looking for is going to be in there. And there's sort of an implicit assumption here that the wavelet tree was created with partitions based on the lexicographical order of the alphabet. So if you'll notice looking at the partitions here, as I previously described, this is how the textbook describes the construction of a wavelet tree. The leaf nodes, if you follow a level order traversal, are going to already be in, I keep saying lexicographical, I'll say alphabetical order. So in this case, our partitions are $A, CT, because that is the alphabetical order. And that's how we know that we should move to the left child here. So moving along, we know that in the range 2 to 8, 4 characters went to this left child, so we're going to look in the range 1 to 4 of this left child's bit vector. And in this case, there's no offset needed because the zeros from the first bit vector, the roots bit vector, went to the left child. And if you look before the range 2-8, we have 2 1s. So in this case, it's irrelevant, but it's possible you could use, or you could require an offset in order to get the proper range to look for in this child. So again, we can count how many elements go to each child in the range. We don't have to use 2 rank functions here. We can just use 1 because we're starting from the very start of the subsequence. So we compute the rank of 0, and that is 1, and the rank of 1, that is 3. Now, since only 1 element will go to the left child, we know the third smallest element is in the right child, so we're going to move there. Moving along, we've now reached the leaf node for A, so we know the answer to our query. The third smallest element in this substring, is A. Finally, I want to give a few acknowledgements, resources I've looked at to create this presentation and to learn about wavelet trees. So Ben Langmead is a computational biologist, and he put out a couple of videos about wavelet trees that helped me to understand the basics. And then I may mispronounce some names, but Enno Ohlebusch, he wrote the bioinformatics algorithms textbook, which I also refer to throughout this for algorithms and various information. Gonzalo Navarro is a computer scientist. He wrote a paper called Wavelet Trees for All that had some interesting ideas in general, but specifically I think I got a lot of the compression information from him. And then 4 people, Robinson Castro, Nico Lehmann, Jorge Perez, and Bernardo Subercaseaux, wrote a paper called Wavelet Trees for Competitive Programming, where I pulled some of the applications from. So thank you for listening. I hope this was informative.